Example 5. Finding induced EMF from rate of flux cutting. Refer to the figure below. The magnetic field lines of the Earth span from the geographic South Pole to the geographic North Pole as shown. When the satellite orbits the Earth above the equator, the conducting tether XY will cut many flux lines. In this case, the magnetic field B is assumed to be uniform. When the tether sweeps across the sky, it cuts the flux lines at a rate determined by the orbital speed. We have to calculate the area that it sweeps per unit time, which is delta A over delta T, where area A is given by D times L, in which D is the distance traveled and L is the length of the tether. D is then given by the speed multiplied with the time taken. And then in this way you will see V and L are constant, and so you will have something like delta T over delta T. Eventually, this delta A over delta T is V times L, speed multiplied with the length of the tether. If you find such derivation difficult, you may actually find the area swept per second. That would also be delta A over delta T, and that will eventually give you LV as well. Hence, the induced EMF epsilon now equals negative delta N phi over delta T, in which delta A over delta T is given by VL, and so we may write it as negative NB cosine theta VL. And since as there is a single tether, N equals 1, and it is traveling in a direction perpendicular to the magnetic field, and so theta equals 0 degrees, and thus we may have BVL to be the answer. For part B, you have to find the relative potentials. You may use right-hand rule to find the direction of induced current, which will flow from Y to X. Thus, electrons flow from X to Y and accumulate at Y, and so potential of Y is lower. On the other hand, you may also take XY as a battery, as induced current flows out from X to the external circuit. X is the positive terminal, so it has a higher potential. Exam link 2. Finding magnetic flux density from epsilon T graph. This is an 8-level question, and no wonder it is in no way straightforward. A rectangular coil enters a uniform magnetic field, and induced EMF is produced as shown on the right. We see that the induced EMF starts at 0.2 seconds. At that time, the coil just enters the magnetic field, and the flux through the coil starts increasing at constant rate. And that's why the induced EMF is constant in the following 0.4 seconds. On the other hand, the induced current drops to 0 at 0.6 seconds. Since that time, there's no change in magnetic flux, and hence no induced EMF. The coil must be inside, totally inside the magnetic field at 0.6 seconds onwards. The area under the graph equals epsilon T, which is, by Faraday's law, delta phi, or simply phi, which means change in magnetic flux linkage from 0.2 to 0.6 seconds, as experienced by the rectangular coil. For part C, you have to find the magnetic flux density B in the equation, Epsilon equals negative NB cosine theta delta A over delta T again, where delta A over delta T is the area swept by the coil per second. As the coil takes 0.4 seconds to move from outside the magnetic field to totally inside, so the area swept per second is given by 0.04 meters square. And then the area under the graph, 1.2 times 10 to the power negative 3, will then be equal to N, which is 1, B, which is the unknown, cosine theta, where theta is 0 degrees, because the area and magnetic field are perpendicular. And lastly, delta A over delta T. In this way, then you may find the unknown magnetic field to be 0.03 Weber per meter square, or simply B equals 0.03 Tesla. Now do check point 3 on the next page.